So my name's Adam. My company that I'm making this project under is called Core Electronics, and let's get started. A little bit about myself is next year I will be studying at Lake Superior State University, and there I will be double majoring in robotics as well as computer engineering. A little bit of my background is I'm primarily a programmer. I started freshman year in game design, then I went up to AP Computer Science, and then last year I took senior projects, and then this year I'm here again. Last year for my project, what I did was I took this part right here, it's called a Vex Cortex. It's the brain for the robot. So you wire everything in through this, you plug the code into here. But the problem with this part is it's $400, which, as you can imagine, gets quite costly very, very quickly. So what I did instead was I took this part called an Arduino Uno, which is a developer board. It's basically a tiny computer that you can use for prototyping. And this and all the parts you need came out to be around $36, so you can make just over 10 of these for the same amount of cost as it would take to buy one. My project this year is same sort of thing. I'm still dealing with robotics. What I'm doing this year is I'm taking a robot and giving it the capability to solve a Rubik's Cube, and the result is what you see before you on this table. The way this works is you take a scrambled cube, you put it into my program, it tells motors to spin the faces, and the finished product should be a solved Rubik's Cube. What I wanted to get out of this was I wanted to keep working on my portfolio, try and get better background, something I can present and say, this is what I've done, this is who I am, you should hire me. I wanted to expand my knowledge of C# programming. C# is just language in programming, a way to tell the computer base instructions of, okay, take this, now here's what I want you to do with it. I wanted to be able to design in SolidWorks, and SolidWorks, as you might know, is a 3D CAD program, which I've never touched because I've been on the computer science side, so I wanted to get some experience in that. Along with that, I wanted to get a CSWP, which is Certified SolidWorks Professional. Sadly, I ran out of time and didn't get to take the test for this certification. I wanted to be able to 3D print custom parts, and that means I can take any idea I have in my head, design it in SolidWorks, and then send it to a 3D printer and actually make it, which seems pretty straightforward, but I'll explain later on in my project. I did run into a few snag-ups with that. And then the last thing, I wanted to create a robot that can autonomously solve a Rubik's Cube, which I made it so that it can solve a Rubik's Cube, but I ran out of time to add the functionality to make it fully autonomous, which means you just set the cube in there, hit go, and it can do everything. For my project, you still have to give it a couple guidelines along the way. To do all this, I needed to research SolidWorks, obviously. I've never touched it, as I said before, so I had to teach myself everything from the base throughout the year. How to solder. Soldering is a way to join wires together using conductive metal, so you heat the metal up and it rests on the two wires and connects them, and it's pretty stable. 3D printing, I said that before, I ran into a few snag-ups, so I had to do research to fix that. Stepper motor drivers and stepper motors. Stepper motors are just a special type of motor, and what these allow you to do rather than a DC motor or a servo motor is it lets you spin the motor continuously, so it's not stuck in a partial rotation, and you can also very accurately set exactly how far you want it to turn. The motors I'm using, you can micro-step them down to 1/8 of 1.8 degrees, so I'm not sure what exactly that number is, but yeah. And then laser cutting, I've never touched the laser before, so I had to research Corel Draw and then just learn about the process of actually cutting the material, which I used for the acrylic box that the wiring is housed in. For this, I used SolidWorks, and Arduino Sketchbook. Arduino Sketchbook is the developer environment. It's where you go in to type the actual code on the computer and send it to the Arduino, which is the computer I'm using. 3D printers, as I've said before, and motors and motor drivers as well. For our projects, we all made pseudo companies. So my company is called Core Electronics. I have a couple different logos. The one on the left is what I used last year. It's sort of low resolution, so I just beefed it up a little bit on the right, and this is what I've been using so far this year. Overseeing all of this, I have Brian Hong, who's sitting over here. Thank you for overseeing my project. He's overseeing the code and the hardware parts of my project. He used to teach at Oberlin, and then from there he transitioned to be SparkFun, which he worked with educators and developing different ways to make students, easy ways for students to learn. And then from there he moved to where he works now. He's back in the classroom and he works at Powell High School, which is a technology-driven high school. So he's, for my support advisors, I have my dad. He's there for financial support. He helped fund my project. I have my brother, who's a web designer, and he helped design my PowerPoints and make everything look nice and neat. And then I also have my peers, Tyler Quinley and Michael Hastings, and they were mainly SolidWorks support. They helped me work through the tutorials and sort of snag-ups that I had along the ways. They also read through some of my project journals to make sure there's no typos or anything that's worded confusing. So for my timeline, we started in October. Before then, we had some introductory work, sort of making our logos, trying to figure out what we were going to do throughout the year. So we started in October. I started mine with just going through the SolidWorks tutorials, getting through the bare basics, so that I knew what I was going to be doing. This took me a couple weeks through October, and then from that I started designing my robot itself. So I started with a way to interface with from the motors to the cube itself, and I did that via these 3D printed parts that sit inside. And then the idea behind this is you can turn the motor and then the face of the cube will turn. But there's a problem with that because this cube, how it's designed, when you turn the piece, you can sort of see it slips past the edges, and then the face doesn't actually turn. So I had to work around that later, and that's how I came up with this. I took just a normal Rubik's Cube and I I drilled holes in it, and then I put dowel pieces that when you turn that, it turns the face of the cube. So after I finished designing everything, I went to 3D printing. So I started with the motor to cube connection, and then the motor plate, which is just a way to attach the motors more securely to the actual body of the robot. And then I started with the size. DRLB is notation that I'll get into later. What that means is I started with the bottom and then the 3 sides of the robot. With this, there was actually a snag up. They didn't actually fit together properly. So I took the entire month of December working to just cut them down, get it so that they can actually slide in and fit together. And then at the end of this, we went into our mid-year presentations, which is just a progress update with the class and Mr. Combs. This is what we've done so far. This is what we have. This is what our final outcome outcomes will be. And then so after we did that, I went back to SolidWorks. I started designing the box that the robot rests on top, and that's just so I can manage my wires efficiently. There's not just a huge mess of tangled wires everywhere. And then so I finished that. That was all the SolidWorks I did for the year. But with that, I haven't touched the code or hardware up to this point. So I started code in about halfway through February. I touched the code. I started researching this thing called the stepper library, which is basically a collection of code that someone else has made so that I don't have to remake everything. It turns out, while I was doing this, I figured out how I'm doing my hardware. I can't actually use this for reasons that I don't really have time to get into. But I spent a couple weeks researching that, and then I realized I couldn't use it. And then at this point, I knew how I was going to do the code. So I moved on and started practicing for my CSWA, which is the Certified SolidWorks Associate, which is a certification you need in order to take the CSWP, which is what my main goal was. I practiced for it, a couple of classes, and then I realized I was quickly running out of time, so I scratched studying for the CSWA, and then I began soldering my circuits. This is just getting everything together, making sure the microcontroller can talk to the motor drivers, and they're talking to the stepper motors correctly. And then through April, I began working on my presentations, which is what we're doing now. For SolidWorks, these are just a few designs I used. This is a mock-up stepper motor that I used, so I knew that when I 3D printed stuff, it would come out correctly. Sadly, I didn't have this idea until after December when I printed about half my robot. So the first 3 or 4 sides didn't turn out. In the middle, what you have here is stepper plate, and that was just a way to secure the motors to the body of the robot because of the tension when the cube sits in there. It actually turns out that I don't need this, and the pressure from the cube will push the motors into the body of the robot without this. And then over here I have the 3D print here, which is a way to connect the axle, which will go on this side, to the cube, which connects on this side. And then one thing about this is there's a slit right here, and the reason I did that was so I could put hose clamps over the end, and when I tighten down the hose clamp, this plastic will actually bend and give it a really secure fit to the axle. This is what all those look like together in real life. You notice it's sort of this weird yellowish color, and that's just because of the material that we used in this print is actually Kevlar, and that gave it a lot of extra stability and extra strength, because when this stepper plate came out, it was only a millimeter thick, which is obviously very flimsy and easy to break. This is the base of the robot in SolidWorks. You can see there's a spot to set each of the sides in, and then there's a little tunnel through here for the wiring of the motor that will sit in here to run through, so that there's a spot for them to go and they don't get cut off when you put the motor in there. This is what a motor and the plate would look like all together. From there we have the sides. This is the first idea. This is what I used for 3 of the sides. And there's a couple problems with this, namely the chamfers, which are these angled cuts on the sides, don't really give the motor enough spot to sit in there and slide in and out easily. So to address that problem, I just took them off in the next design, which is what I used for the last base. And then the other change I made for this as well was in here. Over here, there's not a slot right there, and what that channel does is it just lets the wiring slide in and out with the motors, so they're not getting cut off when you try and put the motors in. This is an exploded view of what the side would look like. So you start with the side, which these pegs right here would fit into the bottom, and then into that you have a stepper motor, and then over top that you have the stepper plate and the connection to the cube. This is 3 of the sides, so the bottom, the left side, and the back. It's just a model of what it would look like if it's put together, which it is. This is a couple design ideas I had for the top of the robot. So I started off with this beam idea that it would rest on top of the just 2 of the sides and sit in there. And I ended up scratching that and going for this more 4-legged design. Mainly just so it's more symmetrical. I think it looks a little nicer. Between the 2, they would both work fine. There's not really any functionality differences. This is just a view with the motor in there. So you notice it doesn't have the stepper plate. I just put holes inside the top, and that's just so I could screw it down, make sure it's really stable in here, and the motor's not going anywhere. This is a complete assembly in SolidWorks, and so you notice it's, after I 3D printed it, it's what you see in front of you. When I 3D printed it, initially there were a few problems, so you can see little cuts that I made with a Dremel tool to make everything sit together. From after that was done, I printed the top and the front, which isn't in there. You notice the mess of wires, which is why I made this acrylic box. And then the last thing with that is I didn't really like how most of it was blue and then other parts were gray. So I put in the last side and then painted it black so it was all the same color, and it just looks nice and sleek compared to how it was before. Before we jump into the code, we should go over notation. So there are 6 sides of the cube, and each cube can be, or each face can be represented by a letter. So the left side will be represented by an L, U will be upper will be represented by a U. Similarly, B will be back, F can represent front, D can represent down, and R can represent right. And so for coding, it's really difficult to make an accurate 3D model. So instead of using a model like this, we can go ahead and unfold the cube, and that gives you something like this. So you have U on top, L, F, R, B are the sides of the cube, and then D can be on the bottom because that's just how it works. And then there are these pluses and minuses on there. You don't really need to know what this is. This is for more technical Rubik's Cube. If you're in the Rubik's Cube, you can probably figure out, but we don't have to get into that. So how my code works is it takes this website, which I actually have right here. And so you go into this website and you go for each spot on the cube. You can say, so for example, this one and this one, all of these ones are yellow, and then you might have some red ones in here somewhere. And then when you finish doing this for all of the sides on the cube, you can see down here solve cube, and this will spit out an algorithm, which is the F2L method. It's just a way to solve the Rubik's Cube, and what you need to know for that is no matter what the configuration of the cube, no matter how messed up it is, it will also always return a sequence of 20 moves or less to solve the cube. This method just is really efficient. It's what most of the fastest cubers use in the world, and it helps to make my robot a lot faster as well. So it takes that sequence, and then it will spit it into my program. You have to manually input that because I ran out of time to make it autonomous. And then my program will break up the sequence and then send it to the stepper motors, which will turn in however the sequence tells you to. And when that's done, you get a finished Rubik's Cube. This is what some of the schematics looks like. This is a little complicated, so we're going to switch to this view, which is a lot easier to understand what's happening. It all starts with this Arduino, which is called Arduino Mega. This Arduino I use specifically because it has a larger computer chip, which means it can do a lot of operations more rapidly. And I'm also controlling 6 different motors, one for each face of the cube. So it starts here, runs the program, and based off what the program I wrote tells it to do, it will send out signals to any of these 6 stepper drivers, which are connected to the motors. And then from this, so the signal can go through the wires and then makes the motors turn. So along the way, I had a couple roadblocks. The main one was 3D printing. So 3D printers in nature, they're not exactly specific. So if you can say you want the material to end somewhere in here. But with that, the motors in the 3D printers won't land exactly on there 100% of the time. So what you get are known as tolerances, which means the material will land slightly on either side of that. So you get a max size and a min size. And so in this example, you have something similar to what I was doing with my sides. Will slide into a hole with a little gap in here. But what I ran into, instead of making a gap right here, I put an exact fit so that it would line up perfectly, and I forgot to compensate for tolerances. So instead of having this max size and min size, what happened was I had a max size that overlapped with this minimum size. So I had to shorten down the shafts and widen the holes so it would fit together properly. One of the other things, this is also due to tolerances, the cube didn't line up properly when we first tried to put it in there. And so how I fixed this was I just drilled a hole through here, and that let me set the bottom's height so you could raise and lower that motor to cube connection with however high you need it so that the sides will line up. And then after this, through testing, I realized that the centers of each side will slide past the edges. And so I scrapped this motor connection system entirely. And then I went to this side, which is dowel pins that are inserted into a Rubik's Cube, and by spinning the dowel pins to the side of the face. This is my bibliography. While that's going, does anyone have any questions?
So, since we're about one question, did it work at all ever?
Almost. So what happened was the code part worked fine on its own, and the hardware part worked fine on its own. But when you try and mesh them together, it doesn't quite work. And then the other problem I had was this is a project that usually a team of people would take on. So one person would be designing in SolidWorks, one person would be working on code, and the other person would be working on the hardware. And I only had not quite a full school year to work on this. So because it was such a massive project for one person and the time restraints, I never had enough time to properly test everything and get it to run all together. Yep.
If you had another year, what would you do next?
So I would start redesigning the 3D prints because how I want it to work is so that it would be completely modular. So you can take this part off, set it over here while you're working. But then if you wanted to, you can take this part out, which since it's an exact fit, it doesn't slide in and out of the bottom. So that would be the first thing. And then once I got it working, I would add in webcams. And with webcams, what that allows you to do is on the webcam, you can fix it at a point and have it look at these three sides. And you can say, okay, so for these pixels, it's gonna be yellow and then yellow, and you want all of these sides to be yellow when you're finished. And then you can see, okay, it's red right now, what do we have to do? And so instead of going through the website and then manually putting that into my program, what you can do instead is have the cameras pick all the spots on the cube, run the algorithm itself, and then hit run, and it would spin the motors and solve the cube. And it just streamlined the process rather than, okay, let's take the time to plug in these 54 spots of information, and then let's transfer that over into a list in the code itself, and then upload that code to the computer. It would be all in one step.
What other applications could you envision this?
So I made this specifically for the purposes of solving a cube. But if you wanted to, you could redesign it for these different shaped cubes. And so that would just take more time designing in the 3D CAD program. And then with that, you would also have the modular ability, which is taking in and off different motors, so that, for example, over here we have a 12-sided Rubik's Cube or a 4-sided Rubik's Cube. You could use the same robot in just a couple minutes switching between. Yeah.
You're going to keep working on this, right? Just to make it work?
Yeah, I'm going to work on it over summer, just to see if I can actually get it to work. And then I'm thinking right now it might be a project that I come back to the future when I finish studying through all my stuff in college. It will be a fun project to come back to. Anyone else?
How long does it take you to solve a Rubik's Cube?
It depends on which one you're talking about. For a normal 6-sided Rubik's Cube, that's a 3x3, so not a small one like this is a 2x2. A 3x3, my fastest time is around 1:15 seconds. Yeah.
If you put one in, actually,
No.
at least
So the motors can spin, but the problem I'm running into right now is, again, with the tolerances in mind, I didn't take that into account when I designed it. So we're having difficulties actually fitting the cube into the robot itself.
All right, thank you.